today we've got Thomas Reek on with us, and he is from Schunk. He is the Vice President of Sales from Schunk. He's been in gripping and handling of parts for over 25 years. So he graduated from NC State University, and he began his career with Schunk in 1994. Made a few changes in there, but ended up back at Schunk. And since he's been at Schunk, he was Director of Sales for the Eastern States, and then gone up to now be the Vice President of Sales. So today he leads a team of motivated professionals, territory managers that are dedicated to serving customers and making Schunk the recognized leader in workpiece handling technology. So Thomas, anything you want to add to that? Again, we are super excited and grateful that you have taken the time to join us here today.
I'm just glad to be here. Thanks for inviting me to participate in your webcast today, and thanks for the great summary.
All right, excellent. Well, we will jump right in. You know, today's main topic, I'm going to let you kind of drive the conversation here. Today's topic is discovering trends toward electric actuators in assembly automation. Obviously, the world as we know it has been primarily pneumatic based, and the trend over the last decade or so has been moving to electric. So very relevant for today's world, and so excited to get into this. Anything to add to that?
Nope. Thanks. If it's okay, if you go to the next slide, we'll say a few things about Schunk, and then
for sure. Tell us about.
Talk about the trends. So just about Schunk, so people that are viewing the webcast know the background. We're a mechanical actuator company primarily, a family-owned business out of southern Germany. Been in business since the late 40s. Initially a small machine shop working out of the family barn, and we've grown since then over 3,500 employees. Wow. Concentrating on robot end-of-arm tooling for grasping. But we also do clamping in terms of fixturing as well. So customers rely on us when they're looking to use robots to move things around. They're also come to us when they're looking to secure parts while some work is being done to it. So if there's maybe a welding process, a machining process, things like that. So the table here is just showing a little bit about the evolution, but in the next slide, I wanted to speak to you a little bit about gripper evolution and how it relates to our topic today. And because we specialize so much in grippers, I tried to use it as the backdrop of a lot of the conversation, but the principles in terms of electric technology, they apply across lots of different actuators and equipment that's used in manufacturing, or particularly automated manufacturing. So
when I started my career at Cummins Engine Company in 1994, that looks like something that we would have done. Or you remember when you have to actually construct the robot using a syringe to activate it. I don't know if you had to do that at all, but it looks exactly like that.
Exactly. Yep. Exactly. So here it's just showing in the beginning in the 80s, I always admire those first engineers that first adopted robot applications, and the fact that they were so successful despite the fact that they had so many challenges that they had to make happen. So just in making any end of arm tool from the gripper, much less complicated end of arm toolings, they had to design the whole thing from scratch. So they had to select and maybe design air cylinders, bearings, gears, and all these parts, put them together, hope it will work, and then run the application and then go on to their next project. And so what happened is, starting in the early 80s, a lot of companies started coming along like Schunk. They're making standardized actuators. So what you're showing here, this is a cutaway of a modern pneumatic gripper today. So it's this concise, very optimized component that applies gripping force and stability to hold the workpiece. It's easy to mount, easy to put sensors on, and does a good job of handling a wide range of parts just out of the box with only designing some small custom tooling to accessorize it. So that's perfect there. What's the standard grippers are mounted out of the box, custom fingers would be designed, and the picture on toward the right, you can see that even with what looks like really small grippers, they can handle really good payloads because these grippers were designed and they're tested, and all the unknowns are taken away because they've all been tested, and the customer can have assurances that it's going to work for their application. So the later trend, or the trend that's continuing with this, is that in addition to the strong mechanics that are already available in the the modern pneumatic gripper, we're also seeing these advanced mechanics that are taking place, like this hand, for example, that gives us all this flexibility. So now we're able to open up to a wider range of applications. We have the technology to be able to control these complex mechanics as well. And then, in addition, the picture that's on the bottom of the screen there, that's just showing the, a simple one-axis gripper. But in both of these cases, what's happening today is we're seeing this combination of mechanical innovation combining with sensor technology, vision technology, software, so that these components are becoming more and more advanced, and customers are not having, or engineers are not having, to reinvent the wheel every time. They can get to their application finished sooner because the components are becoming more and more application ready, not just from a mechanical standpoint, but also from a controls and design engineering standpoint. And that's a big part of where electric driven technology also is fitting in. Many of the people or the engineers that you work with are involved in assembly automation type tasks. And the picture here is just showing what is kind of a traditional example of pneumatic pick and place slides that are servicing various work stations on an index table, where you're progressively performing an operation on a part or workpiece being assembled and possibly tested and marked, and other processes along the way.
Mm-hmm.
And that's very common today, very reliable. But what's happening that tends to cause electrification of these cells are really two main areas that we see. One is just the drive to the application, requiring something that is difficult to do with the traditional way. So it could be, so if you click again, just showing example of different components that are essentially doing the same thing, but through the controls that you have, where say someone needs a faster cycle time, or they're picking up and dropping off to multiple locations, and they need that flexibility. That can, it's often the first reason in the past why people have been going to electric versions, or even hybrid systems where some of the components are pneumatic and some are electric. But even more recently, we've been seeing also people adapting to electric just to optimize their process. So that would just be the next picture, where we're just showing that, again, here we have all electric components. Some of the components can just do the things that pneumatic components would also do as easily, but just for sheer virtue that they are electric, where the customer or the user of the machine can benefit in other ways. So
yeah. So what are those? What are we talking? So orientation, like what are some of the applications that would be unique to electric versus pneumatic?
So if we go back to gripping, for example, one thing that's really common with gripping is that when you have work pieces that have varying sizes, or say you're doing an assembly of a part, you put a gear onto a shaft, and the combination of the assembly together is a different geometry than the part by itself. So you might have interferences and other things that might require you to have that position control, or you might have things that change within the process that might require a force control. So for example, say you're picking up a glass vial and you're putting it into a tray, and then you have to pick up the whole tray. When you pick up the glass vial, maybe you need very low force because you don't want to crush it or mar it in any way. But then when you pick up the box that contains it and other parts, you need a higher gripping force. So with that dynamic control is one of the reasons that drives it or to an electric from a pneumatic, being able to change it on the fly with a certain amount of precision that you can't do with pneumatics.
Get it. Yeah, that makes a lot of sense. Now, the feedback, is it voltage feedback from the electric actuator, and then that's going to determine your torque or the gripping strength?
So it could be predetermined by the customer just through testing based on the situation that's in front of it. It could be that we have force feedback built into the unit or into the device itself that's monitoring to some type of a force.
Yeah, is that now? That was what I was asking. Do you use feedback from the actuation of the motor, or is that a sensor or some type of a pressure sensor that you've put in there? What is your technology that you use, if you can share that?
It's a combination of many things. It could be that in some cases it could be an external force feedback. Sometimes it could be that we're monitoring the motor current. It could be that there are other displacement sensors that are external that are measuring physical distances and workpiece proximity. It's just going to vary application by
It seems
application
like
process.
with electric, you get a lot more. You're able to almost infinite variation. I mean, within reason, right?
It definitely expands the opportunity, and the other thing that I was going to talk about as well is it can also improve performance in many cases, even when you don't need the technological advantages of the electric. Sometimes performance is also a key benefit that can um, that can help the user of the machine.
Then, when you say performance, are we talking repeatability, or are we talking speed, or are we talking both?
It could be both, and it could be things like life cycle. It could be things like speed, things like even sensitivity or reaction time. Think about
Yeah.
pneumatics. Pushing air through a tube. You can push air. Everything's relative. You can push air through a tube. It seems really fast, but when we have applications, if a customer has a very high-speed robot and they have a 1 second cycle time, and we're seeing more and more of those types of applications.
Mm.
We can't wait to actuate a valve that's 15 feet away and push air through 15 feet of hose to close an actuator to be able to grasp that part. We have to have faster reaction time than that.
Yeah, and you don't have to worry about dirty air, moisture in the air. All those things that corrode and cause issues as well.
Exactly. And you know that as well as anybody because you live in Charlotte, where the relative humidity is 98% in the
All
summer,
year.
right?
Yeah.
So this is here just expanding on some of those other advantages outside the technical things that drive um, manufacturers or engineers to go to electric. So if you could just click again. So we talked about a lot of these things just now, but I'll sum them up again for us. So one possible performance advantage is that it can be easy for customers that don't support pneumatics. We're seeing more and more that some types of machinery, particularly training cells and training robots, we see pharmaceutical machines going into drugstores to do pill sorting and packaging, things like that. Machines are going into non-traditional manufacturing environments where you don't have all the air compressors, you don't have the equipment that's prepping the air and keeping the air clean and filtered, as we discussed. Air can be very loud. So having these for certain customers that don't want to support pneumatics, it could be a big advantage, even if the pneumatic actuators would also work.
It seems like in the medical world, it would be very beneficial as well, right? So you're not bringing in those outside contaminants to a clean room and a clean environment.
Yep, that's extremely good point. They tend to be much cleaner, and from Schunk side, we tend to go outside and certify our products to be used in clean room assembly environments, and we find that the electrical products are much easier to achieve those certifications versus pneumatic devices that require some extra amount of engineering to make sure that they're sealed to certain standards.
Yeah, you don't have to use some special grease, huh?
Yep.
Oh, now the intelligent advantages.
So with the intelligent is more what we talked about in the beginning. So these are things that are going to give you more control of your application. So they're going to allow for speed control, for acceleration control, controls forces and torques, position, and all the sensing. So when you have multiple positions, if you're picking and placing to an array of different parts, and a lot of times we're seeing applications where even in our own shop we have in-feeds cells going into a robot line that's actually very basic. They're pieces of wood with cutouts that handle raw materials and space them out. And then there's, depending on the workpiece that's being run that day, the in-feed might look quite different. So you have to have that end effector be able to adapt, to be able to handle the different parts of the different sizes and the different spacing between the parts. So whether you're using a robot or you're using linear actuators to do it, or what type of grippers, having that control is often needed, and electric helps afford you that control. And then in addition to that, we have electric kind of or intelligent divided into two different ways. I showed an integrated intelligent is where the motor is actually embedded into side of the product. And the other type of intelligent that is being highlighted here in this presentation is what we call adaptive intelligence. So that's where the mechanics are predefined, but then the actuator driving the motion, which is typically a motor, whether it's a stepper motor or a servo motor or something else, that's external and is adapted to the device itself.
Now, tell me about so you would need software to program these devices. Is that correct? And does it easily integrate with Siemens and Allen Bradley and any of that? Is it its own module? How does that all come together?
So like with these devices that are shown on the page in front of us right now that have integrated motors or integrated drives, there has to be a handshaking because the Schunk component or whoever the manufacturer is of the electric component, it has to be able to talk to the rest of the machine. And I think one really good thing that's happening in industry overall is that manufacturers and components are coming together, and that bridging between the components and whatever the customer or the user of the machine is standardizing on. So if you have a certain type of field bus network that you want to run the machine on, usually it's not too difficult to be able to get that component talking through that field bus network of the that's being chosen by the machine user. But a handshaking does have to take place. And sometimes that's why people might choose the adaptive technology, because for them it could even be easier. Because if you're using a certain brand, a motor that adapts really well and it's standardized across the whole machine, you're talking to it directly, and you're not having to to integrate the actuator separately from the rest of the machine.
Now, so how do you program these actuators? Is it software that's on a laptop that you plug in and you program, or like you said, it's discrete? Is it? I apologize if you answered that and I just didn't understand it.
I didn't answer it before, and it varies a lot component to component. So some components are as simple as you get. It's just discrete I/O, and you're sending the component a signal. So that goes back to that original thought where if a customer is just looking to put a an actuator inside of a space where they're not looking to use air, but they're looking for all the advantages of electric products. They're looking for the low maintenance and the quietness and you know, other ease of use. Um, they might just need to actuate it using discrete I/O, sending a signal to open or to move left, move right, rotate right, open and close a gripper just through discrete points. It
Mm-hmm.
could be something that has as you described, where you pre-write certain programs that have particular variables that are built into them that could be changed on the fly, but that say for a gripper itself, you can assert a certain move profile command and the gripper will do its thing based on a command and based on some variable definitions that would tell it where to go. And then in other cases that might even be more open than that, where the the actuator is receiving complete information on the fly that's more basic, where it's being told what to do, with how much force or torque with what it's doing.
We've talked about the advantages, and it seems that there are many advantages. What are some of the disadvantages to using electric actuation?
Um, it's also a really good question, Russ. The obvious disadvantages is cost, because you look at the complexity. When you're dealing with pneumatics, I showed you that first screen there, the basic Schunk gripper, that is a reliable product. It's super simple. It's going to, you put air to it, easy to understand. You put air into one port, the gripper closes. You ventilate it and put air into the other port and it opens. And the cost of manufacturing of it can be very easily controlled. 99% of what goes into that gripper is made in one location. But if you're looking at a more advanced actuator, you're going to have all kinds of different components. You're going to have, you're going to have printed circuit boards that are in there. You have controllers. You have communication componentry. Then you have motors. You have connectors. Then you have all the housings and mechanics that all have to be integrated. So there's a lot more complexity, and that drives up the cost, and it also tends to drive up the integration time as well. So it adds to the complexity of the building and the machine. So that's why in the past, usually people only went to the electric as a choice when it was necessary. But now with simpler devices that maybe only use discrete I/O, or they use I/O link and other easy ways of more basic communication to the gripper, that or other actuators, that they may choose to go with the electric products even more readily than they had in the past.
Yeah. So you made me think of another question here is, what about the robustness? If you've got circuit boards, you've got all these different things, and you're putting it on the end of a robot that's swinging around and it's doing its thing. How have you found the reliability to be electric versus pneumatic?
Well, it's interesting. It's the some of the nice things about electric is that with the more electric products, that certain and Industries 4.0, some things can be monitored. That's really nice. That can give you some predictive maintenance, so you can check the heat, any heat buildup in the gripper. You can keep track of number of cycles and things like that. So some ways it's more robust. In other ways, it's less, only in the fact that with something that's more complex, there's more things that can happen. There's more things that can be damaged. But generally, and if you're looking at on a on a cycle by cycle level, our experience is that they're both going to perform the at the same level that the operator of the equipment should be able to expect a very reliable condition in both cases.
Is one now, if you're going into a harsh environment, would that be an environment that you would not want to use electric actuation?
It could be. And it's probably not so much that it's not possible to have good electric products that go into harsh environments, and we do have some.
Hmm.
The advantage that is there now is because, you go back again to that original slide, first grippers were made in the 80s. There were many years where pneumatic products were being designed and optimized for harsh environments and for food handling and for all these other types of jobs. So we have this not just with Schunk, but with dozens of other manufacturers. There are huge catalogs of pneumatic offerings that are
Oh, yeah.
out there that are
Oh, yeah.
standard. And because electric is newer, there just hasn't been enough time yet for them to develop out as fully to be able to handle more of the specialty type applications
Yeah.
the way pneumatics is already available.
That makes a lot of sense. So this is the adaptive intelligence slide I hadn't gotten to because I was asking you a bunch of questions.
No, I appreciate it. You're good. You're a good interviewer. I just wanted to add with the intelligent, whether it's adaptive or it's integrated, it's still, you still get all the same the benefits from a technology standpoint. But the main thing is with the adaptive, by having the motors be able to mount, you get more flexibility. So somebody operating machine, they could conform to different motor brands. So if there's again, say like a gripper, and you have one plant that may use it and the plant across the street may use the same gripper, but one may standardize on, or the two may standardize completely different brands of motors that their in-house teams are comfortable using. So having that flexibility can be better. I also already mentioned the communication can be more easily standardized. And the last thing is you can optimize the motors. When the motor is integrated, that's it. The motor, you have one motor that's designed for it. But it could be that, if the mechanics can take it, it could be that a different motor might want to be optimized for different performance based on the criteria that's in front of it.
So when you say motor, are you talking like what is a motor company name? Like a Bueller that they make motors, or a Johnson Electric makes motors? Is that
I'm
what you're
mainly
talking
thinking about industrial, stepper and servo motors. So you're thinking about, Fanuc, Allen Bradley, Yaskawa, companies like that.
Oh, okay. All right. Very good. So I hadn't, it didn't even occur to me that a company would want a specific motor, but I guess if you have thousands of these in your facility, you're going to want to standardize on something. And so what Schunk has done is allowed, so they're all probably pretty standard interface, I would assume. And because, that industry is standardized on a lot of stuff. So
Exactly.
now, when you order one, do you have to order, if you're going to use a SCAWA, do you have to order an SCAWA interface, or do you just, is the SCAWA the same interface as an Allen Bradley, or?
If we're lucky, sometimes they are. But it's usually pretty simple to design a motor mount and a coupling that would work. That's usually a very short order kind of a adaptation. It's not very complex and very common.
Okay, very cool. Other benefits of electric.
Yeah, so I thought it would be good just to kind of sort it out. You had asked me kind of towards the beginning, like what are the the benefits, and this is really where I was, what I was thinking. If you look on the left, this was a customer that came to us that was doing a machine loading application. They were doing loading the same machine with these totally different types of gears that are stored in different ways.
Mm.
And they're trying to do it at first pneumatic, but the trouble with that is you can't have, even if you have a pneumatic gripper that has enough travel to accommodate all the gears, because of interferences between all the different types of dunnage that they're stored on, they needed that controllability. So they needed to have that. So I was just trying to show having that flexibility to work around the surrounding conditions can be very important. And the asterisk is there as a reminder to me to also say that sometimes we hear from people call us up and they say that they would like to speak to an engineer from Schunk about an electric gripper. And we like to ask them, well, can you tell us a little bit about your project so we can better understand? And one common thing that we hear is that, well, we're handling a large variety of parts, so we want to have an electric gripper that can tell us, do we have part A, B, C, or D? And having encoder feedback from an electric gripper would allow us to do that. And they're absolutely true. You can do that, in one way of handling multiple parts can be done through electric, but also there's very good sensing that's developed through a variety of different companies that allow multiple part sensing, even on pneumatic actuators. So we always try to make sure that people are not looking at over investing in maybe a complex electric product if it's not necessary. So we try to make sure you look at that. If you're only looking for sensing, sometimes external sensors can get you there. The other two things to think about is if you have non-rigid workpiece, so look at the spring clips on the bottom. You think about if you try to grip something like that, you could crush it or closed too far. And so with electric grippers, you can pick up a variety of different springs and only close just a certain amount. You might have to close a different distance on every single part, but based on the part, you only close it and clamp on it a small distance to compress it, only a small amount, so you're not over torquing it or over compressing it. And then, as I mentioned in the beginning, handling marble materials or delicate materials, having really good force control can be important. So with the pneumatics, a lot of times you get stiction in the seals. You can vary air pressure, but you put 5 psi into a gripper, any gripper, it's likely not going to move. Put on 10 psi, it's not going to move. 20, 30 psi, somewhere around 30 psi, those jaws are going to suddenly move really fast, because what happens is the friction that's in the seals is you're going to go from a situation of having static friction to dynamic friction in the seals. And once those gripper gets moving, it's going to move fast. And with electric, you get a lot more control of that movement versus pneumatics around delicate parts.
That makes a lot of sense.
And the last thing is just the big trend, or one of the trends that we're seeing more and more, are companies are looking to get into automation for the first time. And a lot of those times, companies are dealing with lower volumes. So it's pretty obvious if you're a company and you're making fuel injectors and you're pushing 50,000 fuel injectors a day at your door, you're probably already automating. But if you're a machine shop and you're producing 50 of one type of part that has 2 or 3 variances that could change every shift,
sure,
having electric products gives you a much better way to have that adaptability to convert and do those changeovers more readily.
Absolutely. That makes a ton of sense. Sure. So, Thomas, I want to thank you. And as I always end these things, we want to thank our customers. We do not exist without our customers to serve every day. And that's what makes it work. So our mission, again, is to always be adding value to our customers, to our principals whenever we have the opportunity. And Thomas, you have definitely brought the goods today and helping us understand more about electric actuation. And I'm sure it'll be simpler and simpler into the future, easier and easier to integrate, and pneumatics will slowly become like prehistoric Tyrannosaurus Rexes.
Yeah. Thanks, Russ. It was a pleasure speaking with you.
Absolutely. Appreciate you. Thanks, everyone. We'll see you back here at 11:30 next Wednesday. Have a wonderful week. Bye-bye.